section 2.7, we're going to cover inverse functions. Now we're going to start with the definition of inverse functions, which is this. If you have any two functions f and g, in which when you do the composition f of g of x and g of f of x, and both of them give you x as an answer, then that means that the function g is the inverse of the function f, and the inverse is denoted with the symbol f raised to the -1 power. That is read as f inverse, or the inverse of f. Okay. So once again, the two functions are inverses of each other if when you do the composition f of g and g of f, both of them must equal to x. Okay. And then something very important that we're going to cover in the graphs at the end is the domain of the function f is equal to the range of the inverse and vice versa. Now let's go ahead and begin with this. It says find f of g of x and g of f of x and determine whether the pair of functions right here are inverses of each other. So we're going to do the two compositions to determine if the functions f and g are inverses of each other. So we're going to start with the composition f of g. So when I say f of g, remember that means from section 2.6 that we need to substitute the function g, which is x plus 9 over 2, into the x of your function f, into the x or x's, which in this case there's only one x. So my function f of g is going to look like this: 2 times x minus 9, but the x is going to be replaced with the function g, which is x plus 9 over 2. And then we're going to simplify this. Now you can either say multiply 2 times x and 2 times 9, but then if I divide by 2, that's the same thing as saying that the 2's are going to divide out. They're going to simplify. So we're going to be left with f of g of x equals x plus 9 minus 9, and if I combine them, they equal to 0, so that gives you f of g of x equals to x. The next one. Now we're going to do the other composition. Now we're going to do g of f of x, meaning that now we're going to substitute the function f inside of every x of the function g. So the function g looks like this: x plus 9 over 2, but the x is going to be replaced with the function f, which is 2x minus 9. Then what we have to do is we have to simplify this. So in this function we can combine -9 plus 9, which is 0. So you are going to get 2x over 2. But then if I divide 2x divided by 2, that is going to give me x as an answer. So you see that when I did both compositions, f of g and g of f, both of them equal to x. So what does that mean? We can conclude with the following statement. These three little dots means therefore. Therefore, f and g are inverses of each other. So that is my conclusion for this problem, that f and g are inverses of each other. Now the next one, we're going to do the same thing here. We're going to find the functions f of g of x and g of f of x to determine if these two functions f and g are inverses of each other again. So we have to do the two compositions, f of g of x, and we also need to do g of f of x. So f of g of x means that we're going to substitute the function g, which is this 3 over x plus 6, into the x of your function f right here. So then my new function is going to look like this. It's going to be 3 over x minus 6, but that x is going to be replaced with the function f, with the function g, I'm sorry. And the function g is going to be 3 over x plus 6. So then, we're going to simplify this. Now, to simplify this fraction, we can first combine like terms. Negative 6 plus 6 is going to be 0, so we're going to end up with 3 over x. And this is one of the little rules from fractions. You can do this in two different ways. We learned about complex fractions in the previous section, which is that we can, one way of simplifying this is that we can multiply the denominator x on both this term right here and this term right here. Those are the two fractions that we have. And that way we can simplify it. Okay, so if I do that, then I can just multiply the denominator x here, and look what you're going to get. That's going to give you 3x over, and right here the x's cancel out. Not cancel, but they reduce, right? So that gives you over 3. And 3x divided by 3 is equal to x. Or you can also do it this way. This is another way you can simplify this one. Now, when you have division of fractions, you cannot divide by a fraction. Instead, the division of fractions is done by doing the following. You multiply the first fraction times the reciprocal of the second fraction. The reciprocal of 3 over x will be x over 3. That's the same thing as dividing this by this fraction. I multiply this by the reciprocal of the bottom fraction. And that is going to give you 3x over 3, which again, it's going to give me x. So either way, it gives us the same thing. Now, so f of g of x gives me x. But now we need to check g of f of x. What does that mean? We need to substitute the function f, which is this, in the x of your function g, which is down here. So my function g of f is going to look like this. 3 over, and then x, then plus a 6 on the side. But the x is going to become 3 over x minus 6. And then you can do the same thing that I showed you down here. You can do it either way. So I'm going to do it with the complex fraction. To get rid of that denominator x minus 6, I'm going to multiply to this and also here, right here. So what's going to happen if I multiply the x minus 6 here? Let's see. So the x minus 6's simplify here, right? So you're going to be left with 3 times x minus 6 divided by 3 plus 6, right? But then the 3 divided by 3, they reduce, so you are left with g of f of x equals to x minus 6 plus 6, and then if I combine negative 6 plus 6, that is 0, so we get that g of f of x, it equals to x. So, since both of them, f of g of x and g of f of x equals to x, then what can we conclude about these two functions? Therefore, f and g are inverses of each other. And that is my conclusion. Now, for the next part, now I'm going to show you, if I give you the function f or function g, how is it that we can find its inverse? You know, there's an algebraic method that we're going to follow to get the inverse of a function. Now, this process consists of the following. Finding the inverse of a function, of course, given that the inverse exists. Because there are some functions that do not have inverse functions. That's something we're going to cover in the second half. So, given that the inverse of a function exists, how do we find it? Number one, first you need to replace the f of x on the function, or the g of x, whatever the notation is, you need to replace it with y. Change it back to a y. Second step, on the process for finding the equation of the inverse, you need to interchange the x and the y. Every x becomes y and every y becomes x. That's basically what this process consists of finding the inverse. Switch x and y. Step number 3, you need to leave the y by itself. Solve for y. Okay. So after you solve for y, the last step in the process is that you need to replace the y with the f of x raised to the -1. What does that mean? Remember, we went over that on the definition. That means the inverse of f of x. So we're going to rewrite the y with the f of x but raised to the -1, because again that equation represents the inverse equation or the inverse function. Then you can check your answer by doing what we just did on the previous two questions. Do the composition, and when you do the composition, both sides, it must equal to x. And that is just a way of checking the solution. Okay. Let's go ahead and start off with this function right here. The function f of x equals 4x plus 1 is 1 to 1. Now when I say the 1 to 1, I just want you to know that that means that every x has one y and every y has one x. And this has a meaning. When a function is 1 to 1, that means that this function, it has an inverse function. It has an inverse that is also a function. That's basically what the meaning of the 1 to 1, in other words, in easier terms, is going to be. So we are given already that this function has an inverse function. So what we need to do is you need to find the equation of that inverse. Okay? How do we find it? First of all, on this function f of x equals to 4x plus 1, the first step in the process is that I need to change the f of x to a y. So that's y equals 4x plus 1. Second step in the process, we need to interchange x and y. Y becomes x and the x becomes y. That's it. Then my step 3, I need to leave the y by itself. How do I solve for y in this equation? I need to subtract the 1 from both sides. So that gives me x minus 1 equals to 4y. Then I have to divide both sides by 4. Now you can divide on each one by 4, or you can just leave it everything divided by 4. It doesn't matter. So my function is going to end up being y equals x minus 1 divided by 4. And since this equation right here represents the inverse, we're going to rewrite the y with the notation f of x, but raised to the -1, which means the inverse of f of x is equal to x minus 1 divided by 4. And that is the inverse of the function f of x. F of x, x left to the -1 of x equals x minus 1 divided by 4. Now, this is something that you can do extra, which you don't really need to do. It's just a way of checking your solution. What you have to do to check your solution, you have to do f of f inverse of x. In other words, do the composition and see if it equals to x. You have to do it both ways. So I need to do it this way, and I also need to do it like this, by substituting the f of x inside of the inverse. So first of all, let's substitute the inverse inside of the function f of x. So if I replace this function into the x right here, so my new function is going to become 4 times x plus 1. But my x is going to be replaced with x minus 1 divided by 4, which is my inverse. I'm replacing the inverse inside of the function f of x. Now, let's see if that gives me x as a result. So if I do this composition, 4 over 4, they simplify, they reduce to 1, so that leaves me with x minus 1 plus 1, and minus 1 plus 1 is 0, so that gives me x as the answer. So that one gives me x as a result. Now let's check it the other way around. Now I'm going to substitute the function f of x inside of the inverse into the x right here. So my inverse equation looks like this. My inverse equation is x minus 1 divided by 4. But the x is going to be my inverse, my function f, which is going to be 4x plus 1. Then what happens if we simplify this? Plus 1 minus 1 right here is going to give me a 0, so that leaves me with 4x divided by 4, and that equals to x. This is a way of checking if your inverse is correct. you need to do f of g and g of x, or f to f, the composition, substitute the inverse inside of f of x, and substitute f of x inside of the inverse, and both must equal to x in order for that inverse to be correct. Now, the next one. Now we're going to find this. It tells me that this function is one-to-one, and once again, that word one-to-one means that it has an inverse function. So our goal right here is to find that inverse. So let's start with the process of finding the inverse of this function. Step number 1. Given the function f of x equals 9x plus 5 over x minus 6, first thing we need to do is replace the f of x with y. So that's y equals 9x plus 5 divided by x minus 6. Step number 2. The y is going to be changed to x, and every x right here is going to be changed to y. Okay, so we're going to interchange them. Okay, meaning that it's going to look like this. It's going to be x equals 9, and instead of x, now it's going to become a y. 9y plus 5 over x, which is going to be replaced with a y, minus a 6. Okay. Now, step number 3 in the process of finding the equation of the inverse is that we need to solve for y. Now, there are two y's, and also we have a fraction. So, first thing we need to do here is we need to get rid of that fraction. How do we do that? By multiplying the denominator y minus 6 on both sides of this fraction. So that way the y minus 6 is going to divide out on this side, and we're going to have to multiply it on this side. So if I distribute it, that's going to be xy minus 6x equals 9y plus 5. Now, the goal is to leave the y by itself, but if you notice, there is a y here and there is a y here. So we need to put the terms that have the y's, we need to put them on one side. So I'm going to move either the 9y over to the other side or the xy over to the other side. So I'm just going to subtract 9y. So that's going to give me xy minus 9y. But if you notice, the 6, this is to send it over to this side, right? But if you notice, the 6x doesn't have a y. So that one we need to move it over to the other side. So how? By adding 6x to the other side. So that's going to give us xy minus 9y equals 2. The 6x cancels there. So you're going to have 6x plus 5 on the other side. So, how do we finish this? Now we need to solve for y. In order for me to solve for y, you see that there are two y's in this problem. So what we can do, since there's two y's, we can factor out the y. That is our greatest common factor. So I'm just going to factor this y, and if I factor it out, what we are going to have left in here is x minus 9 equals 6x plus 5. Then, how do I leave the y by itself? This one is a multiplication. This one is y times x minus 9. If I want to leave the y by itself, all I have to do is divide both sides by the x minus 9. And that is going to give us the y by itself right here. So that divides out, and we are left with y is equal to 6x plus 5 divided by x minus 9. And now we're going to change the y back to f of x. Since this is the inverse, it is represented with the power of -1. This means the inverse of f of x is equal to 6x plus 5 divided by x minus 9. And that is my inverse function. You can check your solution by doing the composition, and remember, for the composition, it must give you x as an answer. Okay. Now we're going to get into a different idea. Now we're going to look at the graphs, or the graphs. How do we know that a function has an inverse function? This is the next idea in the section. How do we know? By using what is called the horizontal line test. Okay, so when we graph a given function f of x, or whatever the function is called, and if I do a horizontal line test on that graph, and the horizontal line intersects the graph only one time, then that means that that graph or that function has an inverse that is also a function. If I do a horizontal line on the function and any horizontal line intersects the graph more than once, that automatically tells us that that specific graph or that equation that creates that graph does not represent a function that has an inverse function. So we would say that that function does not have an inverse. So we do the horizontal line test to test it. Okay. So out of the family of common functions that we covered before we get into this, which one or which ones do not are functions that do not have inverse functions in general? So let's start with f of x equals 2x. Can I say that this one has an inverse function? Yes, because if I do a horizontal line test, doesn't matter where we draw a horizontal line on this function, the graph is going to be intersected only at one point. Now, we also cover f of x equals to x squared. Does this function represent a function that has an inverse function? The answer for this will be that it doesn't, because if I draw a horizontal line on this function, any horizontal line is going to intersect the function more than once. So this one we say it does not have an inverse function, right? So I'm going to say does not have an inverse function. Now, what about x cubed? Does this function represent a function that has an inverse function? What does it look like? It looks like this, right? This is the shape of x cubed. So it doesn't matter where I draw a horizontal line. This one, any horizontal line is going to intersect the graph only one time. So that means this one, it has an inverse function also. Now, if we look at this one that we also covered, square root of x, does that represent a function that has an inverse? Remember, what is the shape of the square root of x? Like the eyebrow shape, right? So if I do a horizontal line on it, it is intersected only once. It doesn't matter where it's drawn, so that means that this function has an inverse function. And there are two more that we cover, which is, well, three more. Absolute value of x. That one creates the shape of a V. So what can we say about this one? If I do a horizontal line test, that one does not have an inverse function. And if we look at the last one, f of x equals the cube root of x. What do we know about that one? It looks like an S also, but going to the side. So this is basically the shape. It doesn't matter where we draw a horizontal line. That graph is only going to be intersected only once anywhere we draw it. So that one has an inverse function as well. And the last but not least, if I give you a function in the form of a constant, that one, if I that's the way it looks like, right? If I draw a horizontal line on it, what do we know about this one? This one is intersected many times. So what does it mean? That a constant function, it does not have an inverse function. Okay. So let's talk about the other ones. The constant, right now we're not going to discuss it. We're going to discuss mainly all the different types of common functions here on the right side. Now, the majority of them are functions that have inverse functions, with the exception of the absolute value, x squared, and the constant, but we're going to focus on the absolute value and the x squared. Now, even though these functions do not have inverse functions, now something that you're going to see in this section is that we can restrict the domain of this function, just like a piecewise function like that we did in section 2.2. We can restrict the domain so that we only graph a piece of it. And when graphing a piece, when I do a horizontal line test, we want to ensure that the horizontal line intersects the function only once. So for example, what can I say here? What if I say that I'm going to graph x squared only for the values of x that are greater than or equal to 0? That means that the only piece of the graph that we would have is anything from 0 to the right. So from here, which is the middle, to the right. And now if I do a horizontal line test on that half of the parabola, now we can say that it does have an inverse function now. By just doing that little modification, we changed the fact that it didn't have an inverse, but now it does. Okay? This is called restricting the domain. If we do these restrictions, we can get a function that does not have an inverse to actually have an inverse function. Same thing we can do to this one. Okay, the absolute value. So if I restrict the domain, I'm going to do restrict the other way. I'm going to say absolute value of x for any x that is less than or equal to 0. What does it mean by less than or equal to 0? Now that means only the left side of that absolute value, the left side of that v, from the middle to the left side. And now if I do a horizontal line test on that half of the v, that has an inverse function because it is the horizontal line test passes the test. It is intersected only once horizontally. So this is the idea behind whether a function has an inverse function or not. Let's talk about this problem right here. Does the graph given here in this picture represent a function that has an inverse function, yes or no? The answer is no, because if I do a horizontal line test on this function, it doesn't matter where it's drawn, any horizontal line is going to intersect the graph at 2 points. So we can say right here that the graph shown does not have an inverse function. Now you can also say it in a different way. You don't have to specifically say that it does not have an inverse function. You can also say that the graph shown is not one-to-one. Remember, one-to-one means that it has an inverse function. If I say not one-to-one means it does not have an inverse function. Okay? Now we're going to get into the graphs of inverses. How do we create the graphs of inverses? This is the next idea before we go to the end. Keep in mind the following statement, that the graph of a function and its inverse, they are reflected onto each other about the line y equals to x. So let me show you what that means. So that means that, for example, let's say that the graph of f of x, it is just going to be a point. I'm just going to say that point is this one. Let's say this is a point for f of x. This is a function f of x. Just a point. Okay? Now, what does it mean by the line y equals to x? It is a line that has a y-intercept of 0 and has a slope of 1 over 1. So once again, it is a line that has a y-intercept of 0 and a slope of 1 over 1. So that's what the line y equals x basically represents. Okay? So if I have a y-intercept of 0, meaning passes through the origin, and a slope of 1 over 1 means that it increases 1 and goes to the right 1 from point to point. So this is my line y equals to x. I'm just going to make it a dash line right here. This is my line y equals to x going this direction and also going the other direction. Okay? Now, what does it tell me about the function and its of any given function and its inverse? That they both create a reflection onto each other about the line y equals to x. What does it mean? That the distance from this point to the line y equals to x is going to be the same distance from the line y equals to x to the other side. Okay? So which basically you can see that it is approximately right here. Right? So the same, it is just a mirror image over the line y equals x. Okay? And that would be the graph of the inverse function. So what's an easier way of obtaining that inverse function without doing the mirror image? Now look at the coordinates of this point. This point has coordinates 2, negative 2. I forgot a little line here. So 2, negative 2. So to get the inverse of a function, all we have to do is we need to interchange the values of x and y. Because if I do that, what is that new point going to become? -2, comma, +2, which is basically the point that we have labeled right here. -2 and +2. Okay? So that's how we get the mirror image over the line y equals to x, by interchanging the values of x and y on the points of the function to get the points for the inverse function. Now, let's take a look to this function given here. We are going to use the graph of this function to sketch the graph of its inverse function. So this function given right here, we're going to call it f of x. So what do we know about f of x? F of x passes through the points right here, -5, -5. It also passes through the point, this one, which is -1, 2. It also passes through the point, this one, which is 3, 1, 2, 3, 4, 5, 3, 5. So those are the 3 points that we can see exactly on that graph. So if I want to sketch the graph of its inverse function, all I have to do is you need to interchange the x and the y values for the function f of x to create the graph of its inverse. So -5, -5, it's still going to be -5, -5. -1, 2 becomes 2, -1, and 3, 5 becomes 5, 3. So when we sketch this, -5 equals -5 is going to stay the same. 2, -1, it's going to go right here. And 5, 1, 2, 3, 4, 5, 3, it's going to go up here. And this is going to be the graph of the inverse function. Now, I want you to take a look at why. What is the reason of the why this -5, -5 did not change? And the reason is because if I do the y equals x line, this is your y equals x, -5, -5, it's its own reflection. So that point is exactly on the line of reflection, meaning that it is its own reflection. That's why it doesn't change. But as you can see, this point is reflected to this side over the line y equals to x, and this point is reflected to this side over the line y equals to x. They reflect to each other over y equals x. And that's how you sketch the graph of an inverse. Now, for the last 3 questions that we're going to do in this section, now we're going to combine all the information that I provided to you from the previous parts. We're going to combine them into the following problems. Given this function, f of x equals to x to the third power minus 6, I want you to find the inverse of the function, graph the function f and its inverse in the same plane, and use interval notation to give the domain and the range of both the function and its f of x and its inverse. That's what we want to do. Those are the 3 pieces that we're going to answer here. So, we are going to begin by finding the inverse of that function, letter A. So, to find the inverse of a function, right here the first thing that we got to do is that we need to replace the f of x with the y. So that gives me y equals to x raised to the third power minus 6. Next one. Now we need to interchange the x and the y values. So the y is going to become x and the x is going to become y. So we get x is equal to y, and of course that one is being raised to the third power minus 6. And the last step here is that we need to solve for y. So how do we solve this for y? I need to first move the 6 over to the other side. So we're going to get x plus 6 equals y raised to the third power. And what did I mention? The opposite operation of the exponent is going to be the root. So in order for me to simplify the third power, I need to take the cube root on both sides of this equation. Okay, so the cube and the cube root, they simplify each other because they're opposites, and that's going to leave us with y is equal to the cube root of x plus 6. That is the inverse of this function. So now we're going to change that back. Remember, since this represents the inverse, we need to replace the y back to f of x, but it's going to be raised to the -1 power, which it is read as the inverse of f of x equals cube root of x plus 6. So that is part A, the inverse function, which is the cube root of x plus 6. Letter B. For letter B, what we have to do is that we need to graph both f of x and its inverse function. So I am going to start by graphing f of x. So we know that f of x equals to x cubed minus 6. So what I need to do is I need to pick my values of x as usual to graph this function. And for any function with the exception of the square root and cube root, keep in mind that we use the points -2, -1, 0, 1, and +2. So when I substitute them, this is going to be -2 to the third power minus 6, then -1 to the third power minus 6, 0 to the third power minus 6, 1 to the third power minus 6, and the last one is 2 to the third power minus 6. So -2 to the third power, it's going to be -2 times -2 times -2, which is -8. Minus 6 is going to be -14. So then, the next one, -1 times -1 times -1 is -1. Minus 6, it's a -7. Then, 0 times 0 times 0 is 0. Minus 6 is -6. Then, 1 times 1 times 1 is 1. Minus 6 is -5. And 2 times 2 times 2, that's going to be an 8. Minus 6 is going to be a +2. So, for the function f of x, I'm going to put it right here. We got the points -2, comma, -14, -1, comma, -7, 0, comma, -6, 1, comma, -5, and 2, comma, +2. So let's go ahead and sketch the function f of x. I'm going to extend my graph a little bit right here, so it goes to the 14th, okay? So it can reach -2, comma, -14 is going to be down here. The next point, -1, comma, -7, it's here. Then we got 0, comma, -6. Then we got 1, comma, -5, and the last one is 2, comma, +2. So remember that the function x to the third power has a shape similar to a snake shape, or an S shape. So we connect this point. This is what the graph is going to look like approximately, and it keeps on going both to the left, to the right, up and down. Right? It just keeps on going. Okay. So this is the function f of x. So what we are going to do next is that we are going to graph the inverse of this function f of x. How do we sketch its inverse? By interchanging the x and the y values. So if I want to get the inverse function right here, all I need to do is interchange the x and the y values. So that one becomes -14, comma, -2. All I'm doing is interchanging the x's and the y's. -7, comma, -1. -6, comma, 0. Then -5, comma, 1. And the 2, comma, 2 is going to stay the same, 2, comma, 2. So I'm going to extend this a little bit right here. So 11, 12, 13, and 14. So that point is going to be -14, comma, -2, which is going to be down here. The next point is -7, -1. The next point is -6, 0. The next point is -5, +1. And the last one is 2, comma, +2. Now, if I ask again, why is it that 2, comma, 2 did not change? because remember that these graphs must be reflected onto each other over the line y equals to x. And what is the line y equals to x? It is the line that has a y-intercept of 0 right here, and it has a slope of 1 over 1, 1 over 1, and so on. So if I do the line of reflection right here, we're going to notice that the point 2, 2, it is exactly on the line of reflection. So it reflects to itself, basically. It creates its own reflection. So this is my line, y equals to x. And we can exactly see that all of the points here, they are reflected onto each other over the line y equals to x. This point reflects onto this one, this point reflects onto this one, and so on, and so on, and so on. Okay. Now, this is the answer for letter B, the graphs of f of x, and of course the inverse of f of x, which is the pink one. How do we finalize this? Now what we need to do is we need to find the domain and range of both of them. So I'm going to do f of x right here. We're going to find the domain and we're going to find the range. And then we're going to do the inverse right here. We're going to find the domain and we're going to find the range. Now, if we look at the blue graph, this blue graph, which is f of x, it keeps on going to the left side, which means that all of the negative values of x will be on this curve right here. So -3 will be down here on the graph, -4 would be down here on the graph, and so on and so on. Also, you see that it keeps on going also to the right side right here, which means that 3 is on the graph, 4 is on the graph, 5 is on the graph, and so on. So all of the negative and positive values of x will be on the graph, meaning that the domain is -infinity to +infinity. By definition of inverse, keep the following in mind. If the domain of f of x is -infinity to +infinity, that also means that the range of the inverse function is also -infinity to +infinity. The domain of f of x is the same as the range of the inverse function. Now, let's find the range of f of x. This graph keeps going all the way down, which means it goes all the way to -infinity on the bottom. And this graph keeps also going all the way up right here. So that means it's going to go all the way to +infinity at the top. So what does that mean? That the range is also any number from -infinity to +infinity. And since the range of f of x is from negative to +infinity, that also means that the domain of its inverse, it is the same as the range of f of x, which is -infinity to +infinity. And that concludes this problem. We needed to find the equation for the inverse. We needed to graph both f of x and its inverse in the same rectangular coordinate system. That was part B. And C, we needed to find the domain and range of both functions. And that concludes this problem. The next problem. Now we're going to be given this function, f of x equals the square root of x minus 10, we're going to find the inverse of this function, and then we're going to graph both the function and its inverse, and we're going to use interval notation to give the domain and the range of both. So, letter A, we're going to find the inverse of this function, f of x equals to the square root of x minus 10. In order for us to find the inverse of it, what we need to do is first we need to change the f of x to a y. So that's y equals to the square root of x minus 10. Then we need to interchange the x and the y right here. So that means that the y is going to become x equals to the square root of y minus 10. So that's going to become a y right here. And our last step in the process is that we need to leave the y by itself. So, in order for me to leave the y by itself, I cannot get rid of the 10 yet. The first thing is that we need to get rid of the square root here. Eliminate the square root. What is the opposite of the square root? Second power. So in order for me to get rid of the square root, what we're going to do is we're going to raise both sides of this equation to the second power. that is going to give us x to the second power equals to y minus 10, because the square and the square root, they simplify. So then we're going to solve for y by adding the 10 to both sides, and so y is going to be equal to x squared plus 10. Then we need to change it back to the notation of f of x, but since this is the inverse function, then we're going to represent it with the -1 power. That means that the inverse of f of x is equal to x squared plus 10. And that is my inverse function. Letter B. Now we're going to graph both f and the inverse in the same rectangular coordinate system. Now I'm going to start with the function f of x. To get the graph of f of x, the first thing we're going to do is we're going to create a table for that function. Just keep in mind that since this one it is a square root, whatever number we substitute into the x, it must give us a perfect square. So what are the perfect squares that we want to get right here? I want to make sure I get the square root of 0, square root of 1, square root of 4, and square root of 9. So what value do I substitute here so that when I subtract 10, it's going to give me my perfect square 0? It is going to be 10. So when I substitute it, then I'm going to get 10 minus 10, which is going to be a 0, and the square root of 0 gives me 0. What perfect square can I substitute? What number can I substitute into the x so that when I subtract 10, it's going to give me my perfect square 1? So 11. So right here is going to be the square root of 11 minus 10. That's going to give us a square root of 1, and the square root of 1 gives us a 1. What number do I substitute here so that when I subtract 10, what does x has to be so that when I subtract 10, it gives me the next perfect square, which is 4. 14. So if I substitute it, that's going to be 14 minus 10, it's going to be a 4, and the square root of 4 is going to be 2. And the last perfect square would be 9, so I need to substitute a 19 so that when I subtract 10 from it, it's going to give me the square root of 9, and that is going to give us a 3. So for the function f of x, we're going to get the following points: 10, 0, 11, 1, 14, 2, and 19, 3. Remember that we're trying to get a perfect square, and not only that, we're trying to avoid negatives because the square root cannot give me a negative number. That's the main thing. Okay, so let's go ahead and graph this. So we're going to have 10, 0. For this one, I think I need to increase the sketching a little bit. So I'm going to increase this graph until the 20, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay. I'm going to do the same thing on the top right here. I'm going to increase it all the way to 20. So that's 11, 12, 13, 14, 15, 16, 17, 18, 19, and then one more, 20. So those points, 10, 0, it is going to be here. 11, 1 is right here. 12, 13, 14, 2 is right here. And the last one is 19, 3. 14, 15, 16, 17, 18, 19. So 19, 3. And this is the graph of f of x. Remember that the square root has the shape of an eyebrow. So that is f of x. Now let's find the inverse. How do we get the inverse points? The points for the inverse function. What I need to do is I need to interchange all of the x's and the y values. So that's going to become 0, 10, 1, 11, then 2, 14, and 3, 19. So let's go ahead and graph those. 0, 10, it's going to be right here. 1, 11, it is going to be here. Then 2, 14, 11, 12, 13, 14, that's going to be here. and the last point is going to be 3, 19, 14, 15, 16, 17, 18, 19. So 3, 19 is going to be right here. And once again, this is the shape of my inverse. And just to keep you informed and to keep for yourselves to keep this in mind, the graph of f of x and its inverse must create a reflection onto each other over the line y equals to x. So if I reflect each one of these points onto the line y equals to x, this one is a reflection of this point, this one right here is a reflection of this point, and so on and so on and so on. All the points create a reflection onto each other. Okay. So we already got the first two parts, which is we found the equation for the inverse, and then we graph both the function and its inverse. The last thing that we need to do is we need to find the domain of f of x and range, and the domain and range of its inverse function. So that would be the last part of this. So if I look at the blue graph, what is the domain? The domain is that it starts from 10 and it keeps going to the right. So that means it's going to start from 10, including the 10, and then it's going to go all the way to the right to infinity. Remember that we also learned from a previous section, 2.6, how we find the domain of a square root. We have to say that the inside has to be greater than or equal to 0, right? So if I solve for x, that is going to tell you that x must be greater than or equal to 10, which is basically the same as from 10, including 10, to positive infinity. Now, what do we know about this? That since the domain of f of x is from 10 to infinity, that would be the same as the range of its inverse. So the range of its inverse will be 10 to infinity as well. Now, let's look at the range. What is the lowest value of y on this graph? So the lowest one is going to be right here in the middle, which is 0. That is the lowest value of y. Now, what is the highest value of y? It is going to be infinity, because this graph keeps going all the way up, so it's going to reach infinity all the way to the top. So the the range is from 0, including 0, all the way to infinity. Now, since the range of the function f of x is 0 to infinity, that also means that the domain of its inverse is also going to be 0 to positive infinity. And that concludes this question as well. We're going to answer one more question about finding the inverse, graphing both the function and its inverse, and given the domain and the range. Last question is going to be this. This question in particular is a question that I focused when I was mentioning to you the horizontal line test. How do we determine that a function has an inverse function? And we talked about this function particularly, x squared. We said that x squared just itself does not have an inverse function. But in order for me to make it have an inverse function, what we needed to do is restrict the domain so that we can show only one piece of the function. And that's exactly what we are doing right here. We are restricting it so that we show only one piece of that parabola so that it has an inverse. Okay? So, in order for me to find the inverse, let's go through the process. Letter A. Okay. So, to find the inverse, first we're going to change f of x to y. So that gives us y equals to x minus 5 squared. So then I need to solve, interchange the x and the y. That's the second step in the process. I'm going to interchange these two. So the y becomes x right here, and the x right here is going to become a y. And the last thing we're supposed to do is we need to solve this equation for y. So how do we leave the y by itself? Well, the first thing that we need to do before I can move the 5 over, I need to get rid of that square. And the opposite of squaring, if you remember, it is the square root. So what we need to do is take the square root on both sides. The square and the square root, they simplify each other. They're opposite operations. And remember, there's only one thing that I ask you to remember here. Whenever you do the square root on both sides, This is called the square root property. The solution is always going to be plus or minus. So, if now this is going to be plus or minus the square root of x, and that equals to y minus 5. But if I want to solve for y, I need to move the 5 over to the other side. So that's going to give me y is equal to plus or minus the square root of x plus 5. There is something that I do want to mention though about this problem that is very important for you to know. So, if I go to the, let's say, the graphing calculator. Let's put this in the graphing calculator and let's analyze some stuff from this function. It did not get opened, so let me do it again. Okay, so let's go ahead and do this. If you go to the y equals and you graph that function, that plus or minus means that you have to graph two functions, the square root of x and then plus 5, but also plus 5, but also we need to do the negative square root of x and then close parentheses plus 5. There are two pieces on this function, and just to differentiate them, I'm gonna go to the left side and I'm gonna bold that one, the second one, the one with the negative square root of x. The other one will not be bolded. So look at both pieces. It gives me this and that. What would you tell me if I actually graph the whole picture? If I give the whole equation as it is. When graphed, what do we notice? That if we do the vertical line test right here, what can we say? That this is not a function because it intersects the graph at 2 points. So this is an example of an equation that does not represent a function. So we need to be careful on this one because that's why we have the restriction in the domain. When we actually graph it, when we get the equation of the inverse of the x squared, there's only one piece that will be on the graph of my function. It would be either the positive square root or the negative square root, because both of them together, they give me a function, an equation that is not an inverse. That is not a function, I'm sorry. Okay, this is not a function, so we cannot have this. So before I go into basically how we can determine which one it is, I'm gonna go ahead and graph f of x, and from there I can show you. Okay, let's go ahead and create the graph of f of x, then we're going to finish this part on determining if it is a plus or a minus, the one that we need to have for this function. Okay, so for letter B, we're going to create the table to sketch the graph of f of x. And f of x equals x minus 5 to the second power. So let's create the table. -2, -1, 0, 1, and 2. So if I substitute this x, that's going to be -2 minus 5 squared. Oh, wait a minute. But I also made a mistake right here. So I forgot what's called the restriction. We need to make sure we follow that specific restriction. I forgot that. What is the restriction in the domain right here? It tells us that x must be a number that is less than or equal to 5. What does it mean? That the table is going to include 5, 4, 3, 2, 1, 0, and so on, and so on, and so on. Let's go ahead and do this 4 points. Okay. So if I substituted 5 minus 5 and then square, that's going to be 0 squared, which is going to be a 0. The next one, this is a 4, so it's going to be a 3. 4 minus 5 squared equals to -1 squared, which is going to be a 1. Then 3 minus 5 squared, it's going to give us a -2 squared, which is going to be a 4. Then 2 minus 5 squared, it's going to be -3 squared, which is going to give us a 9. And so for the function f of x, some of the examples for the points that we can see would be 5, 0, 4, 1, 3, 4, and 2, 9. So 5, 0 is going to be right here. 4, 1, it's here. Then 3, 4, it's right here. And then 2, 9. So you see that when we graph it, the only piece of the graph that we see here, it's going to be the left side of the parabola. Right? This is a parabola, but we only have the left side of it. Right? And that has an inverse, right? Because if we do the horizontal line test, the graph is intersected only once. So this is the function f of x. Now, how do we graph its inverse? We're going to interchange the values of x and y. So the inverse should be 0, 5, 1, 4, 4, 3, and 9, 2. So when we graph this, 0, 5 is going to be here, 1, 4, and then 4, 3, and then 9, 2, which is this one right here. And that would be the graph of its inverse. It is like an eyebrow, if you keep that in mind, because it is a square root. Okay. Now, the only thing I'm concerned about is on the two pieces. You see on the inverse that we graph, that's all we see. Which is the only piece that we see on the inverse function? Do we see this top or the bottom piece? It is only the bottom piece. So, which one creates the bottom piece? Is the negative square root. Now, how can we determine that it's going to be the negative but not the positive? Just remember this, that whenever I have the square root of x, is the shape of a regular eyebrow. What does the negative in the front do? It makes the function to reflect over the x-axis, over the x-axis, as you remember from the transformations. So the one that we can see right here is the reflection of the regular eyebrow, which is the negative square root. That one, that's what we call it. Okay. So in this one, when we discuss about the plus or minus, then in this one it's just going to be a negative square root. That's the equation that identifies as this curve on the bottom, as the eyebrow being reflected underneath. So we got the equation of the inverse, we graph the function and its inverse, and we need one more thing on this. We need to give the domain and range of both f of x and its inverse function. So we're going to do f of x, we're going to find the domain and the range, and then the inverse of f of x, we're going to find its domain and its range. What is the domain of this function, the blue one? You see that the graph keeps on going to the left side. So what does that mean? That it's going to start from negative infinity, and where does it stop? It stops at 5. So my domain is going to be from negative infinity to 5, but it's including the 5. So you're going to put a bracket at the 5. Since the domain is negative infinity to 5 for f of x, then that means that the range of the inverse function is also negative infinity to 5. Remember that the domain of f of x is the same as the range of the inverse, and the range of f of x is the same thing as the domain of its inverse. Okay. Now, let's find the range of f of x. The range, you see that the lowest value of y right here, it is 0. And this graph, what is the highest value of y? Since the graph keeps going up, that means it's going to reach all the way up to infinity. So it's going to go from 0, including 0, all the way up to infinity. So it's going to be bracket at 0, comma, infinity. And since the range of f of x is 0 to infinity, what does that mean? That the domain of its inverse, it is also 0 to infinity. And these are the domain and the range of both f of x and its inverse function. So we got A, B, and C. This problem concludes the section 2.7, which is inverse functions.